Okay, so now we're gonna oh, actually totally forgot we need to do this question, part C. Um and so it's converting the other way. So taking the B tree that we just got, this one, after inserting 13, 17, and then converting it back to the red black tree. So this is going to be pretty similar to question 1 when we did the opposite, red black tree to B tree. So let's just, I think it's part C. We're just going to use this as a reference. I don't want to draw it again and make it cleaner. So, okay, let's start at the root node, because why not? So the root, this one is a pretty easy node, right? It's just 14. So it's just 14 there. So actually, let me step back for a second. The general way we're going to approach this is it's going to look almost exactly the same as what we have here, except these three nodes, this one, that one, and this one, they're all going to have a red child, because if they were all singletons, and by singleton I mean, like, for example, 27, it just has one element in the node. If they're all singletons, then making the red black tree is super easy, because you just draw all black nodes. But when there are stuff like this, like doubly stuffed or even triply stuffed nodes, then you need to introduce red nodes. So we'll get to that part when we go on the right child. But let's just do the left one for now, because they're all easy ones, right? 14, 12, 8, 13. That's just basically just copying it. So 14, 12, 8, and then 13. And I'm not really doing arrows here. I guess I could, but I think it'll be quicker if I don't. Okay, now we'll do the right child. Okay, the right child is what? It's the doubly stuffed node. So we need to convert this 2531 child, or node, into we need to convert the 2531 2-4 tree node into a valid left-leaning red-black tree. So remember, like we talked about earlier, there's kind of a conflict, right? Because which one do we make the root? Do we make it look like this on the left, or the one on the, let me point to it. Do we make it look like this, or do we make it look like this? Because it's a left-leaning red-black tree, we're going to make things lean left. So we take the one on the left. So let's convert that. So that means 31 is going to be the root. I just realized I don't have much space. 31 is going to be the root of that, like, in the converted tree. And the child is going to be it's going to be a red child. So it looks like that. Okay. Now we're just going to continue from here. So let's do the 17, 19 doubly stuffed node. So the left child of 25 is going to be the whatever the root is of that node. In this case, it's going to be the 19, because remember we're going to make it left leaning, which means the child is going to be the 17, and it's going to be red. Okay. Now we can do the 27. So the place the 27 goes, it's just like, if you kind of imagine this is its own node, kind of, right? This little 25 inside the doubly stuffed node, and it has a left child of 17, 19, and its right child is 27. So that means here it's also going to be 27, like that. So you might think that also, oh man, I can't scroll up now. Well, okay, I can't scroll up for some reason, but you might also think that, oh, well, why can't 27 be the left child of 25? And it could, except because we're doing the left child of 31. And then it could, but because we're doing left-leaning red-black trees, that actually wouldn't work, because the left child of 31 is already taken, right? It's taken by the 25. So that's just another, I guess, reason why 27 belongs there. Okay, now we can do the right child on the right of 31, and maybe if I do this. Well, okay, I think I have let's see, 33 and 46. Okay, I just wanted the numbers. Okay, so the next thing on the right child, it looked like this, 33 and 46. So, just like the other doubly stuffed nodes, the 46 is going to be the root. So 46, and it's going to lean left. into a red child. That's going to be the 33, just like that. And actually, maybe if I go like, maybe if I do that. Okay, cool. That nice, that worked. So yeah, that your red black tree is gonna look like that. And you can kind of double check your work by remember that in part 1 when we converted from the red black tree to the 2-4 tree, we sent up the red nodes. So it's gonna, let's see, if I send up the red nodes, then this 25 gets squeezed into there, this gets squeezed in, and that gets squeezed in. And then if you kind of look at it, then you'll see that, oh, it actually ends up looking exactly like the B tree we were given. So you can kind of imagine this 25, like the red node being side by side with its root node in the corresponding like B tree. Okay, yeah, so now we can move on to some, check mark that. Now we can move on to the analysis questions. So, okay, someone gives us a 2-4 tree, and now we want to get the keys in sorted order in worst case linear time. Okay, so let's recall first how we did that in a binary tree or binary search tree. So let's just draw that. It looks like something like this. And it could go on. So remember that what we did in this case is we did an in-order traversal, where first we did, kind of had some list. We had some list. And it had a bunch of elements. So first we insert all the elements from the left child of the root. So maybe that fills up like this many. Then we insert the root itself. And then we insert all the elements on the right side. And maybe it's that many. So we did, what this is called is an in-order traversal. Because first you recurse on your left child. So that would be this child. Then you add yourself, which corresponds to this. And then you recurse on your right child, which is this stuff. So that's how it worked in the binary search tree. But in the, what's called B tree, we have more nodes. So that, like for example, this node has 4 children instead of 2. But it's still you can still kind of use the same algorithm for the same in-order traversal, except you need to modify it a little bit because, nodes have more than 2 children. So let's draw an example B tree. I'm not going to write the nodes in. Let's say it looks like that. And then maybe some more, dot. So we're going to do the same thing where we definitely want to add all the things on this child first. But then, so you actually, let me do this. So yeah, we're going to insert all the things from that child first. And then we'll insert, the guy at the root. So then the person at the root. And then its right child, you can think of, is the next one in line. So this child, maybe that points to another one, and it goes on a little bit deeper. And then you actually need to go to the next item in the root, right? And then, again, you take whatever child is next, add that, and then go to the next item in the root, and so on. So you can kind of think of it as like, in this case, because there's 3 elements in the root, you can kind of think of it as 3 different in-order traversals. So first it's like if this was like 1, this was 2, this was 3, then, that would be there. And then a separate binary tree where that's 2, and then a third one where that's 3. And you kind of do these 3 different in-order traversals. So we didn't really have to write any pseudocode for this question. You're just kind of describing it at a high level what you're doing. So you can kind of, I guess you could write something like let's say, X different traversals where X is the number of elements in the root node. And that would definitely get you like credit if this is an exam question. And then in terms of the runtime, because the in-order traversal was linear runtime in how many nodes there are, this is actually going to be the same thing because we're just doing the same linear traversal, and we're not really going to any element more than once or twice maybe. So because every element's only visited once or twice, it's still going to be linear runtime because nothing's getting looked at multiple times. So if we're looking at everything just once and there's n things, that's going to be theta of n, which is in O of n in the worst case. So we're in the runtime requirements. So that one, let's just write do x different in order traversals. Okay. So if a 2-4 tree, blah blah blah. Okay, so this is relating the this question is kind of just saying why. Let me actually do this. This question is saying why the red black tree still has the same runtime requirements, or sorry, runtime it has the same runtime requirements on the operations. So for example, and the reason why that's not immediately obvious is, like, if you look at this B tree, it's perfectly balanced, right? There's all the leaves are at the same level. It's only height 2, but in the corresponding red black tree, it's not quite balanced. So like here, this one has a height of, what is it, 1, 2, 3. This one has like height 4, but this leaf only has height 2. And these ones are 3 over here. So it's not quite balanced. But as after we answer this question, you'll be able to see that even though it's not quite balanced, it'll still have the log n operation runtimes for like insert and search and whatnot. So okay, let's start. Actually, we can just use this tree to kind of analyze. So what makes the right tree like worse than, like by right I mean this child here? What makes that 31 subtree worse than the 12 one? So we know that the right one has a higher height, and the reason is because of these, like, the red nodes, because the red nodes add 1 to the height, right? Because remember that in the B tree, this 31, sorry, it was 31, 25, or sorry, 25, 31. So this is like this node here. In the B tree, we could have those be at the same level, but in the red-black tree, we can't. So we need to do this thing with where we have a left child being red, left child because it's left-leaning. So this actually gets converted to 31, 25, and where that's red. So we just added 1 to the height because the normal red-black tree could support 2 in a single node, but the 2-4 tree can support 2 in a single node, but the red-black tree can't. So the key to this question is understanding that the red nodes are what kind of mess you up, increase your height. And specifically, every red node increases your height by 1. Okay, so with that in mind, let's read the specifics, because I kind of forgot. So the 2-3 tree has, we can actually do it here. So the 2-3 tree has depth h, and blah, blah, blah. And how many comparisons in the worst case does a red-black tree need to know to find a certain key? So I hope you understand that the second part of that question is basically just asking, what is h, I'll call it h prime, where h prime is like the height of the red-black tree. Because we know that the worst case number of comparisons is just the height of the tree, because the height of this tree is 4 because that's the biggest height, and in the worst case we would be searching for 17, right? So that would take the most time because that's the most number of comparisons, which is also just equal to the height, right? Because to get a 17, you need to do 1, 2, 3, 4 comparisons, and then you're at 17. We don't really include the checking equal to 17 as a comparison, so that's why it's 4 and not 5. Like, it's not like once you're at 17, like, check if it's equals. Okay. So basically, what's the height of this new red-black tree? Well, because we know that adding these red nodes makes the tree larger, in the worst case, we have every node is as stuffed as it can be. And because it's a 2-4 tree, that means every node has 3 elements in it. So, if a node has 3 elements in it, then it's going to look something like, it's going to look basically like this, right? So this node, which gets converted into this. So it adds 1 to the height. So even though, so basically if it's a double stuff node or a triple stuff node, it still adds 1 to the height. The only difference is that the triple stuff node adds, so it has a left and a right child. So it has the 12 and the 31, whereas the 2531 node just has the 25. So actually the right child here wasn't so bad, or it wasn't as bad as the other one, because this one's height 3, right? If this was triple stuffed, then this would also be height 4, because there would be another red node right before the 46. So basically, it doesn't matter if it's double stuffed or triple stuffed. It could be triple stuffed will definitely be more, but like asymptotically, it'll be the same, right? In the worst case. Okay, so we know that. Okay, so we're gonna write. So I'll just say triple stuffed. So all 3 stuffed nodes. So that means it's gonna add 1 to the height for every red node, and there's gonna be 1 red node for every black node. Well, actually 2, but because the 2 red nodes are on different trees, so they're not going to interfere with each other, right? Like, just because there's 2 red nodes here, that doesn't increase the height, right? It matters about, let's just pick one. Let's just pick left and figure out the height of, the worst node there. So because it adds 1 to the height for every triple stuff node, and there's the height was h in the B tree, we're only going to be doubling the height. You can kind of think of it as like for every node in that path of the B tree, you actually need to do 2 comparisons, because one for that node, one for for example, here, if we just pretend it's double stuff for now, in the B tree, we could get away with just going from here directly to a child, but in the red-black tree, we actually need to compare to the 25 and then the 12, right? Because 12 is the red node. So it's just doubling all the comparisons you need to do. So we'll say h prime, h prime is equal to 2h. So, and that's actually not that bad, because it's not like we increased the height by anything related to n. We're just doubling it. And we know that in a 2-3 tree, h is going to be equal to log of n. So in the red-black tree, h prime is going to be 2 times log of n. And we know in our bounds, theta bounds, O bounds, omega bounds, we just drop the constant anyways. So it's still going to be log n. So all the operations are still going to be log n, and that's because of the height. Because the height is some multiple of the height of the of the B tree. Okay, so that's that was part D and part E. So we're good there. Okay, so the next video we're gonna be talking about the try question here.